So I'm Shawn Wei. I'm a seismologist from Michigan State University, and I'm glad to share some of our new recent observations in Alaska using onshore, offshore seismic observations. And first of all, I want to acknowledge my a lot of co-authors. As you see here, the first three are my students or former students, and also my colleagues at MSU, mainly like geodesists, and also my colleagues at the USGS and University of Science and Technology in China and the University of Arizona and the UC Berkeley. So I want to start with this cartoon, and I believe you have seen some similar cartoons many times. It's about the Earth's deep water cycle in subduction zones. The general idea is that the downgoing plate, so we call it slab after it's subducted, gets hydrated near the outer rise, and then in the form of hydrous minerals or even just pore fluids, and then once the plate is subducted to greater depths, and the water will be released in all kinds of processes like compaction or dehydration, metamorphic dehydration reactions, and then water will return to the surface to form a volcanic arc. And over here, I want to, in this talk, I know it's only 50 minutes, I want to touch three topics. One thing is about the fluids in the megathrust, and also I will talk a little about the fork, because that's where we believe fluids coming from subducted sediment compaction and modulating megathrust slip. That's where a lot of large devastating earthquakes happen. And the second part is the slab deep dehydration. That's usually we relate those to intermediate depth earthquakes. And then the third part is subarc melting and in the mantle wedge and also in the crust that feed the volcanic arc. So my focus here is Alaska Peninsula. There are a couple of reasons why we want to study this region. This the zooming map. I have to warn you through my talk. There are a lot of regional names. Some Russian names, some local Alaska names or American names. So I don't expect you to remember all of those. But I hope you get a general sense. This is a place that we see a lot of long strike variations in earthquakes and volcanism. For example, over here on this map, these dashed contours outline the megathrust large earthquakes happened in the last century. And as you see, this we call the Shumigan Gap. Why there's no earthquake happen or no large earthquake happen in that part. And also by looking at those triangles, those are arc volcanoes. And in terms of eruption activity, they also vary a lot. For example, they are more active in the southwest and less active in the northeast. And also there's a geological discontinuity called the Becher discontinuity. Of course, we know there are a lot of variations in all subduction zones, but it's interesting over here is that the incoming plate is relatively uniform in terms of the age, in terms of the convergence rate, in terms of the convergence direction. But why we observe changes in the volcanism and the earthquakes? So one hypothesis that's proposed more than 10 years ago, led by active seismic work by Donald Shillington, was they proposed based on two active seismic profiles over here. So line 5 and line 3, they proposed that the incoming plate in this region varies a lot. For example, in Shumigan Gap, as you see, the mantle, the slab crust, and also the slab uppermost mantle has a lot of, they observe reduced velocity interpreted as water or hydrous minerals over there, whereas in the midi segment to the northeast, then the uppermost mantle is not that hydrated. So they propose that there's more water when I say water is quoted, so that could be hydrous minerals subducted in the Shumigan Gap. That's why in this region in the southwest, we see different volcanism and seismicity compared to the surrounding regions. And also, led by that hypothesis, we also did a study mainly based on onshore observations, more than 30 years of seismic stations in this region, Aleutian and Alaska, seismic data, and also we look at the geochemistry. So this slide, I have to apologize. This is a very busy figure, but I just want to show that we look at seismicity, earthquakes at different depths. We look at double seismic zone, which is a unique feature for in subduction zones. We look at the B value of earthquakes, which can tell us something about fluids. We also look at geochemical signatures from volcanoes. But the general idea is that we believe there's more water subducted in the southwest and less water subducted in the northeast. And then we drew this cartoon, as you see that the slab is hydrated to a degree that the blue shade indicates the extent and the intensity of dehydration, where in the northeast there's much less, and we even add a yellow layer indicating sediment over here. But you probably realize that the cartoon here misses a lot of things. There's no upper plate. There's no mantle wedge. But anyhow, our hypothesis is that we think, okay, in the subduction zone plate, the subducted slab is important. That probably can control all the things, can explain all the things along strike. Is that true? Well, luckily, there was this amphibious community experiment in Alaska. So there were 75 ocean bottom seismometers deployed in this region, and many land stations. All of those are showing us the black dots over here for about 1 year. And after those deployments, earthquakes always happen after we finish one deployment. So there were 3 large earthquakes happen in this region, and those are just those black contours are the rupture areas of these earthquakes. And so, using this data, we actually can image what happened before these large earthquakes, or in seismology we call it interseismic period. And so a lot of names over here, but I want to just briefly explain what we do very quickly. So one part we do travel time tomography. This is very standard technique, and mainly done by my former student, Dr. Fan Wang. And so these are all the seismic earthquakes we use, all the seismic stations we use. Try to image VP and VPBS ratio. And also, this is another work by another former student, Dr. Yachi J. We develop a new technique called the FaceNet TF that we focus on spectrogram to detect earthquakes. And turns out it's very useful for detecting earthquakes recorded by OBSs, because we know that horizontal channels of OBSs are always noisy. So it is actually more effective to look signals in the time frequency domain. That's why it's called TF. And so we from there we have a better earthquake catalog. And we also try to image seismic attenuation, which is different from seismic velocity and tells us some other constraints about the rock properties. This is led by my current students, Joy and John. Okay, so like I said, first I want to touch this megathrust region and see what's the role of fluids. And for a long time, we always try to look at we always try to look at the plate interface. This cartoon model which have been cited, I don't know, thousands of times. We basically, I think these two models that's talking about the same thing is that the physical properties, especially fluids on the plate interface, that control megathrust seismicity, like the locked seismogenic zone, why we have tremors down deep, why we have shallow tsunami earthquakes up deep, why a lot of things can be explained over there. But you notice that over here, the overriding plate is really just simple, it's blank. Does it matter? Well, initially we like following by the hypothesis I mentioned earlier, we try to look at the slab and the interface. And so these are some images. We just quickly jump to some conclusions. So over here, these are VPVS ratios. I know this is just blue and red colors. What do they mean? I try to skip a lot of details, but for short is that we please look at the high VPVS ratio. Blue colors probably indicate high fluid content, whereas the red colors probably indicate low fluid content. Then over here, you see a lot of changes along this slide surface or plate interface. And by if we zoom into focusing on this 2020 seminar magnitude 7.8 megathrust earthquake over here. So this is the hypocenter where rupture initiates. And this black curve, so this is the plate interface. And this black part is actually rupture region. So from this earthquake, we see that it's it coming from the water-rich region and ruptured the entire water-rich region. That's interesting. That's actually what we expected. But so what's interesting is 1 year later, even larger earthquake. You see on the map view is the northeast of Seminole earthquake is called Chigny earthquake over here. It initiated, yes, in the water-rich region. You see the blue color over here on the megathrust. However, it ruptured into a red region, which is water starving region. So the rupture area is actually much larger. So that means that the water, yes, that probably can fluids can initiate rupture, but that's the fluid distribution does not define the rupture area. And we are also very interested in the interseismic slip plate coupling. So on the right side on top, this is plate coupling means that right before earthquakes, so how the upper plate moves relative to the lower plate. The red colors means that the two plates, the downgoing slab and the upper plates, are fully coupled. That means it has a higher potential of having bigger earthquakes in the future, where the blue color over here means that there's almost free slip. So we don't expect large earthquake to happen. There could be a lot of small earthquakes. So for a long time, we believe in this is actually indicates the fluids. However, if we look at the seismic tomography imaging we have, this is the plate, overriding plate, and also the plate interface. Well, I know a lot of information. I try to simplify those into these cartoons. The general idea is that if we look at the southwest, for example, Shumigan segment, we see a lot of fluids at plate interface. We see a lot of fluids in the overriding plate, and the interseismic slip deficit is low. So that's what we expected. However, for the rest of segments, we don't really see a strong anti-correlation because we usually think, okay, if there's a fluids at the interface, then there must be low plate coupling, but we don't really see a strong intercorrelation between the fluids at the plate interface versus the plate coupling. Instead, we see the fluids in the overriding plates strongly anti-correlate with the interseismic slip deficit. So that's why for this part, we think fluids in the overriding plate rather than on the plate interface actually controls interseismic plate coupling. And this is actually supported by after the earthquake catalogs. So as I mentioned, we use deep learning to detect a lot of aftershocks after these earthquakes. And these are just some vertical cross sections. I would invite you just to focus on these red symbols versus the green symbols, because those are aftershocks after two different large earthquakes. And you can clearly see that after the Seminole earthquake, the red symbols, there were way more aftershocks in the upper plate versus compared to the red symbols after the Chigny earthquakes. The short is that again, it supports the idea is that in the Shumigan, in the southwest segment, the upper plate, the overriding plate crust is more deformed, more hydrated, and probably by supplied by fluids from slab dehydration. So that's megathrust. Let's go a little bit deeper to the deep dehydration. And also I want to directly go up to see the subarc melting. So this time the real question is we know of course a lot of allostrike versions in the surface arc volcanism. What controls that? Is that slab deep dehydration or something in the crust? And these are the images on the velocity VPVS ratio and also attenuation, P wave attenuation on the right. As you can tell, is that right beneath the volcano over here, there are some along strike changes. I want to jump to the cross sections. Probably that's easier to see. For example, this is the Pavlov volcano. It's a huge volcano to the southwest. It's even eastern part of the Aleutian, and we can see a lot of low velocity, high BPVS ratio, and high attenuation in the slab and also beneath the in the mantle wedge, and indicating a lot of melt in the mantle wedge. And actually, by the way, that's actually consistent with the recent EM's observations as well. As you see, there's a lot of mantle dehydration in the slab over here. But if we look at Aniakchak, also a huge volcano, but we don't see much melt, as you see from attenuation and also VPVS ratio. We don't see much melt in the mantle wedge, although the temperature is high. But if we look at the Trident volcano, which is smaller, again, we see a lot of melt in the mantle wedge. A moderate mantle wedge. So this is along strike cross sections along all the volcanoes, as you see over here, from southwest to the northeast. The general idea, these black curves are the mole of overriding plate, and also so this in between is the mantle wedge. The idea is that yes, we do see a lot of mantle wedge melting in the southwest and also in the northeast, but not in the middle. But when we look at volcanic activity, that's a different story. So for volcanic activity, it's actually divided by this discontinuity called the Bachelor discontinuity. All the well, I won't say all, but generally speaking, volcanoes are more active to the southwest and more active to the southwest and less active to the northeast. But if you look at crust, you suddenly see this dramatic change in the crust structure right across this discontinuity. Therefore, we propose that it's actually not mantle wedge, but also the melting. But eventually the crustal processes that controls volcanic eruptions. So this is a summary. I just want to go back to our hypothesis at the beginning. As you see this cartoon, I only had the slabs because at that time we try to find is there a simple solution that the variations in slab can explain everything in the in the subduction zone. Well, that's the time we didn't have offshore observations. Now with the offshore observations, the story is definitely different. In terms of interseismic plate coupling, the fluids we believe, at least in Alaska, is actually more important in the overriding plates that compared to that on the plate interface or within the slab. That modulating plate coupling. And for volcanic eruption, we believe the transcrustal processes are probably more important than the mantle wedge. So these are lessons I learned, and I think all the offshore, I know this is seafloor observation seminar. So yeah, all the offshore observations can always revolutionize or always change our ideas. That's the end of my talk. Thank you.